All right, so last time, fractional saturation. We defined the equation for fractional saturation of a protein. So theta, which is the fraction of bound protein, is equal to the ligand concentration over the ligand concentration plus the Kd. Right? Now, looking at this, I want to see some implications, right? One that will come out, I guess I'll go ahead and tell you now, is this. The Kd, by definition, is a concentration. And it is one particular concentration of this equation of um, P plus L goes to PL, right? So this is in terms of concentrations, whatever it is, micromolar, millimolar, or whatever. Ligand concentration is obviously also in terms of concentration. So the Kd is a concentration. And so we really are thinking about this in terms of the ligand concentration. So the ligand concentration relative to the Kd. And so let me show you how to use this equation, and then we'll do some plots and see kind of what the implications are. All right, so theta is equal to ligand concentration over the ligand concentration plus the Kd, right? And so what happens when the ligand concentration is equal to the Kd, right? Since they're both expressed in terms of concentration, we can do that analysis, right? Well, if L is equal to Kd, then theta becomes what? Well, we can take this in any direction. So I said here that L is equal to Kd, so I'll keep it there. So then theta is equal to the Kd over the Kd plus the Kd, right? And so here, theta is equal to Kd over 2 times the Kd. And I actually just expressed this relationship with my 11-year-old son dealing with apples and oranges or something like that for his class. They're learning algebra now. And so he struggled with this concept. So theta here is equal to Kd plus 2Kd, or over 2Kd, or we can eliminate these Kds to say theta is equal to 1/2, right? So we can define a concentration at which you have 1/2 bound protein, right? And so we can define the Kd as it's equal to the concentration, well, this is redundant, at which you have 1/2 protein bound. Well, this should kind of look familiar, right? What did we define the pKa as in acid-base chemistry, right? The pKa is what? The pH at which you have a 50-50 mix of acid and base, right? And the math here is basically exactly the same. The pKa is equal to a pH, so the terms are the same, at which you have a 1-to-1 ratio. In this case, the Kd is defined as the ligand concentration at which there's 1/2 protein bound. And mind you, for any given chemical reaction of protein to ligand, there is one specific Kd, right? There's only one. And that actually becomes a descriptive characteristic of the reaction at which is at work. Let's just do a couple more of these just to get the hang of it. So let's go back here. I'll change my color to purple because, prints. Theta is equal to the ligand concentration over the ligand concentration plus the Kd here. Why don't we say that the ligand concentration now is equal to, I mean, were we in a live class, I'd have you give a number, but let's just say 4 Kd, right? So the ligand concentration is equal to 4 times the Kd. When you do that, you have 4 Kd over, so theta, so 4 Kd over 4 Kd plus a Kd, which would be equal to 4 Kd over 5 Kd, right? So the Kd's cancel, and so that theta at this point is equal to 80%, right? So the ligand concentration is 4 times the Kd, you have 80% maximal binding. Let's just kind of do one more here. When theta is, when the ligand concentration is equal to, let's say, 10 times the Kd, right? Well, let me just say 9 to make the math easy. Then theta would be equal to 9 Kd over 9 Kd plus Kd, which would then be equal to 90%, right? 9/10. Okay, so a couple of things should be apparent, right? If we had a linear relationship, right? We said that when the ligand concentration is equal to Kd, then we have 50% bound, right? So if we had a linear concentration, then when the ligand concentration is equal to 2 times the Kd, you would have 100% bound. But let me just put this in red. That is not the case, right? When the ligand concentration is equal to 2 Kd, then you end up having 66% bound, right, for theta. And I would leave you to do that math and try that out. So something breaks down. And in fact, you have to go up here. We have the ligand concentration is 9 times the Kd, not twice the Kd, but 9 times the Kd, and still you're only at 90% bound. So if you plot this out, it's going to look something like this, whereas you increase the ligand concentration, at some point you actually level out, right? And so you approach 100% bound here, but you never actually reach it. And so I only have a minute left, but let's go back to our slides. And this is what we see. And all of this is just kind of what we pointed out before. This is a plot of fractional saturation. So as you increase the ligand concentration over here, you see that you get a dramatic increase, but it levels out at 100%. It approaches 100%, but never hits there. And we can define a KD. So by definition, if you go to where you're at 50% bound, you can define a KD, which is a concentration in which you have 50% protein bound. And mind you, so this is the same ligand, and so we have A plus L goes to AL, two different proteins. B plus L goes to BL. Shoot, let me just do this in green for consistency's sake. And if you were to plot these out, these have different binding affinities. And we know this because when we plot these values out, and this is a function of their KDs, let me say A here and B here, we see that they plot out differently, right? And so here we see protein A over here, protein B over here. We can measure the KD simply by going to 50%. We don't need to know anything about this. We just go to what's bound at 50%, and we see that protein A has a KD of 10 nanomolar, and protein B has a KD of 60 nanomolar. And just by looking at this graph, we know that protein A has a higher affinity for the ligand than protein B, right? Because what? You get to 50% bound at a much lower concentration than you do for protein B. And in fact, if you look over here at the concentration in which you're at 50% bound for protein A, 10 nanomolar, I mean, this doesn't really say, but it looks like you only have about 15% bound for protein B. So protein B is clearly has lower binding affinity than protein A. And so just by looking at the graphs and the empirical evidence, you can get a sense of how the protein binding chemistry works in these protein ligand interactions. I will stop here.